But you also still have to go to class. But like, you do that.
I will begin with a word of prayer. So, Heavenly Father, we thank you again for this opportunity we have just to meet together and study your creation. Pray again that the students would understand more about math here and that they would ask good questions as they have them, Lord. In your name I pray, Lord Jesus. Amen. So we were talking about sequences. So I have an example or two more to show you. So sequences. So example 1, I could have a sub n equals to, let's say, c r to the n for n equals to 0, 1, 2, and so forth. All right. So if I were to list it like this, it would look like you got your c, then cr, then cr squared, and so forth, cr cubed. All right. This guy has a name. This is called the geometric sequence. So let's see here. How would you tell if a given sequence is a geometric sequence? Like, how could you characterize it?
If it's a variable to the nth power.
If it's a variable to the nth power, right. Let's see here. Let me think if I can think of one here. How about this one? If I have, you know, let me think here. 4, 12, 36, I heard a 108. I'll take that one. So is this a geometric sequence? So there's always a question, right? If you're just given the first few terms in a sequence, is it really enough to establish a pattern, you know? And so, you know, admittedly, there's an ambiguity there. I mean, you could have different sequences which have the same start and have a different end, right? So asking, here, you know, here's a list of numbers, find a formula for the numbers is always, I mean, that's a question that you can ask as an instructor, but it's not really that interesting of a question either. But here's a way. If this is geometric, the thing to notice is that the ratio of any two subsequent terms must be the so-called, you know, r, the ratio, if you will. All right, so like, check this out. If I look at 12 over 4, what do I get? If I look at 36 over 12? If I look at 108 over 36, right? They're all 3, right? So this, in some sense, you could use to define a geometric sequence. Sequence is geometric if what?
All ratios are the same.
If, yeah, exactly. If a sub n plus 1 divided by a sub n is equal to r for each n in the sequence. For each index, for each index n, let's say. Right? And in this setup, the c is just the first thing. If you're starting from 0, c is just the first term. Okay? So like this, you could write as, this is just the sequence 4 times 3 to the n equals 0 to infinity. All right? This is the geometric sequence. So that's an example. Another example, which is a little bit weirder, I'll fit it in here. Example 2, we could have, let's see here, here's my sequence. Let's call it b sub n, just use something else. And here's how it's going to go. 3.1, 3.14, 3.141, 3.141. I got to look. You guys tell me what comes here. 5. What's the next one? 1, 4, 1, 5. Yeah, you guys are right. So what is this? What is this? What's this sequence here?
I where n
Yeah, right. So this is, so here we're forming a sequence by, you know, b sub n is equal to the decimal representation of pi to n digits, or n decimals, I should say. Right? And here I'm starting at 1, since I said it like that. So the first decimal is the 0.1, right? Then you have 0.14, that's 2 decimals. 0.141, 3 decimal digits, so forth, yeah? So anyway, that's, I literally can't give you a formula for this, right? You could use the digits in pi as a random number generator if you wanted to. There's probably easier ways to make a random number generator, but there you go. I mean, once upon a time, you'd find mathematicians who would be holed up in a shack somewhere, and they'd spend decades calculating more digits of pi. Like, there were people who did this for a career. Who paid them? You know, I don't know. And like, I don't know, I guess the sad thing is if you're that kind of person and you get a digit wrong somewhere. Well, the thing is, yeah, how would they know? Yeah, I guess right. How would they know? That's a good question. How would they know? Maybe they wouldn't. Maybe that will come to light after their death, right? Whatever. So I think that did happen, yeah. But anyway, so next up, here's a definition. So, you know, we talk about lots of different kinds of limits of functions, right? Limit as x goes to the right. Limit as x goes to like a from the left, from the right. Limit as x goes to infinity. Limit as x goes to minus infinity. There's a bunch of different kinds of limits we've talked about for functions of a continuous variable, right? So what we're looking at right now are functions of a discrete variable. Why the variable's discrete? Because it jumps, right? Like the n jumps from 1 to 2 to 3. There's no what's the 1.5th term in the sequence is not a question we even entertain, right? Sequences are labeled by, you know, integers, right? They have to have a start, but they don't have to have an end. So there's really only one interesting limit here to talk about, which is the limit as it goes to infinity. And here's how we define it. If for each epsilon greater than 0, there exists n in the natural numbers for which n greater than n implies the absolute value of a sub n minus L is less than epsilon. Then we say the limit of the sequence a sub n is L, and we write a sub n goes to L as n goes to infinity, or equivalently, the limit as n goes to infinity of a sub n is equal to L. All right. Such a sequence is known as a convergent sequence, right? If L in R as above exists, then AN is convergent sequence. Right? Otherwise, the sequence is said to be what? Divergent. Right. So, yeah?
What does big N mean? N is greater than N.
Oh, so here, let me draw a picture for you guys. This is not in the notes because pictures take me a lot of time. So I have not gotten to the point of putting pictures in your notes. So all the pictures will be in here, but not in my typed notes, all right? But what would the graph of a sequence look like? Here, let me make a concrete one. Something like, here I'll do a sub n equals to 10 plus 1 over n squared. Right? So at 1, where is it? I mean, not 10. Let me do 3 plus 1 over n squared. So make it 2. I'll get it eventually. 2 plus 1 over n squared. So here's 1, here's 2, right? Let me look at 1, 2, 3, 4, 5, 6, 7, 8. Oh, so, okay, all right, fine. So a sequence, the graph of a sequence is kind of boring. It's not usually a useful thing to do. But if we go to 1, what happens? We plug in 1, we get a sub 1 is 1 plus 1 over 1, which is 3, right? So the graph starts out like here. Here-ish, right? So here's 3, yeah, this is 2, 1, right? So there's the first thing, there's A1, which is 3. Then when we get to 2, we get 2 plus a quarter, which is 2.25, right? So there it's about here-ish, right? 2.25. When we get to 3, 1 plus 1/9 is what? About 2.1-ish. So let me see here. Let me try to, it seems like 2 is going to be an important thing here. So let's make a little dotted line here for 2 so you can follow my, my picture better. And instead of using blue, I'll use a different color like green so you can see it. All right, so, all right, we're starting out at 3, then we drop down to 2.25, then we drop down to 2.1, right? And then, golly, I mean, up to the limits of my artistry, it's pretty much just right above the line, right? I'll make the dots bigger so we can see them, but you see what's going on here? So what's the limit of this sequence? The limit of the sequence is 2. Now you're asking me about what the n is, right? So it's different things for different epsilons. The n, conceptually, this n is a function of epsilon. All right, so typically a function of epsilon. All right, so for my example right here, suppose your epsilon is a half. All right, suppose your epsilon is equal to a half for the sake of discussion. All right, and because that's pretty much the only thing I can illustrate here. What does it mean? What is this inequality up here? What is this saying? What does this say if epsilon's a half? What are we looking at here? What does it mean? Absolute value of a sub n minus, and apparently our L is 2, right? What does this inequality mean here? Can somebody tell me in terms of distance what that means? Yep.
A sub n minus the limit, so that's the difference between a sub n and the limit is less than epsilon, so it approaches n.
No. Specifically, what does this mean?
It's closer to the limit than.
No. There's no closer here. Specifically, this means, let me ask you a different question. What does this mean? If I say the absolute value of b minus a is less than 7. So Sam is trying to get ahead of me. He's answering a more interesting question. What's that?
The difference is less than 7.
The difference is less than 7. No, what does it mean geometrically? What is the absolute value of b minus a? If I put b and a on the number line, what can you tell me about them? I don't think that's true. It could be 1,000,000 and 1,000,006. What's that? They're within 7 units of each other, right? In other words, to put some words in your mouth, this is the distance from a to b, right? The distance function. The absolute value of the difference of two numbers is the distance between them. So the way to understand this inequality, what this is literally saying is the distance between 2 and a sub n is no more than a half. Does that make sense? So I can illustrate that with a band. See, L is equal to 2, and the a sub n's are the green dots, right? They're the y values of the green dots. So to say that a sub n minus 2 is less than a half is to put a band of height 2, half, 1/2, right? Like here. Probably should have used a different color. Sorry about that. My bad. Anyway, it is what it is. So the width of that band, right, is what? How this band. Up here you're looking at L plus epsilon, down here you're looking at L minus epsilon, all right? So what is the quote-unquote n equal to here? I can change the definition a little bit. Let me change the definition a little bit. Well, I guess, I mean, listen, guys, you could put n greater than n, or you could be n greater than or equal to here. Nobody probably would much care. I guess I'll leave it greater than, though. I did write that. So, look, the n here, I can just put basically right here. If I put n equals to 1, right? If n is greater than 1, that implies that, 2 plus 1 over n squared minus 2 is less than a half. In other words, past that point, the absolute value of a sub n minus 2 is less than a half. Right? A sub n minus 2 is 1 for the first point, and after that, it's at most a quarter. Right? So for this choice of epsilon, my n would just be 1. Now what if I make epsilon equal to 0.01 for my example? In other words, I'm trying to figure out what would I'm trying to, here's my a sub n minus L, right? Which in this case is 2 plus 1 over n squared minus 2. I want that to be less than 0.01. Right? Just for the sake of discussion, all right? The 2's cancel, and this gives you, we need the condition 1 over n squared is less than 0.01, right? So we can find an equivalent inequality. This is, interchangeable with what? 1 over 0.01, right, is less than n squared. Which is what? 100 is less than n squared, which is equivalent to saying 10 is less than n. In other words, more like I want to look at it, n is greater than 10, right? So we can choose n equals to 10.
Because there is an absolute value, should be plus or minus?
No. Because the thing we're taking the absolute value of is manifestly positive. And n here is, well, anyway, even if n were negative, it would still be, n is positive here, but even if n were negative, it would still square to, anyway. But so in this case, if we chose 10, if you go 10 out in this sequence, that means if you were to go beyond 10, you can be sure that the values in the sequence are within 1/100th of the limiting value. So to prove that the limit of the sequence is L, you have to be able to do this for arbitrary epsilon. Right? So none of what I've written so far proves that the limit is 2. All right? But I think you can pretty much see what you do, right? If instead of putting 0.01 here, you put epsilon, right? So this is not in the notes just because you guys asked me a question when this happened. So anyway, so if I instead of putting 0.01 here, I replace this with, say, epsilon, right? And you track this. This is basically going to go to, n is greater than 1 over epsilon squared, right? So I believe we could do this. Let epsilon be greater than 0. Choose n equal to 1 over epsilon squared. Observe for n greater than n, we have the absolute value of, let's see here, 2 plus 1 over n squared minus 2, right, is equal to the absolute value of 1 over n squared, right, which is equal to 1 over n squared, right, which is what? This is less than 1 over n. How do I know that? I'm assuming what? That n is greater than big N, which means if we make the denominator smaller, we've made the fraction larger, right? But then, what is n equal to? 1 over epsilon squared. Aw, man. My bad. I should have done what?
Is epsilon supposed to be 1/2 power?
I should have put oh, this is supposed to be squared here. My bad. So that's one thing. That's supposed to be squared because I had 1 over n here, and 1 over n squared would make it smaller. And in light of that, you see my choice was wrong. What should I have made my choice? And in fact, if you go over here, was our n equal to, like, look at back here. What did I actually do? This was actually 1 over the square root of epsilon, wasn't it? Because the square root of 0.01 is 0.1. So actually, and this happens as you're writing proofs, like in this realm, is you make a mistake, and then as you write out the proof, you find out, oh, that's not quite right. So how do I need to fix this? Instead of putting an epsilon squared here, I should have put a what? Yeah, if I just put square root of epsilon. The thing is, you've got control over that. You can pick the n however you want. That's the game we play here. And so that's actually 1 over epsilon, yeah? Which is also known as epsilon. OK, so thus the limit as n goes to infinity of 2 plus 1 over n squared is equal to 2 by definition of the limit. And so this is, I suppose this was all example 3, wasn't it? Now, you will be delighted to hear me tell you this is not how we typically calculate limits, right? So I'm showing you how the definition operates in gory detail for an example. We're not going to keep doing this, right? Because, goodness gracious, it would be annoying. Now, in the notes, I worked something simpler. In the notes, if you look at my example 1.9, you'll see I just did it for 1 over n squared, right? So in the notes, pretty much the same argument works for 1 over n squared. So similarly, can show the limit as n goes to infinity of 1 over n squared is equal to 0. All right. So this is the definition, nonetheless. Let's move on here. OK, so before I erase this, though, question. And I definitely don't want to do the epsilons and deltas because it would require a technical definition of pi over here, right? Any questions about this? Yeah.
Sorry, maybe you said already. Where did you get the a n equals 2 plus 1 over n squared?
That was given. Basically, the problem is this. Given what's in the green box, calculate the limit. And since you guys are asking me about it, what does the definition mean? So I was trying to elaborate on that. What it means is that if you go far enough out, you can get as close as you want to the limiting value. If the limit exists, you can make the values of the sequence arbitrarily close to the limiting value by going sufficiently far out. So how about this one? Like I can't do epsilons and n's for this because, again, it would require a definition of pi. But you can see intuitively what the limit would be there, right? What's the limit of b sub n? Yeah, exactly. My bad. Limit as n goes to infinity of this one would just be equal to pi. So for math majors, this is actually an interesting example. And you guys math majors? It's not too late. There's still time. You can add the math major. No? Hey. Let's see here. All right, let me try to pick up the pace a bit in here. So the next thing to prove about a sequence is that if a sequence is convergent, it is bounded. All right, what do we mean by bounded? So A sub n bounded means there exists little m and big M real numbers such that little m is less than or equal to A sub n is less than or equal to big M. All right? For all n. For all n in the, the domain of the sequence. So this is bounded. Alternatively, you could say bounded means this. It means that the absolute value of A sub n is less than or equal to some m for all n. So you can either go one way, you can do either this or that as your definition of bounded. Different people do different ones, but they're equivalent, okay? They're equivalent. Now, so how do we know the convergent sequence is bounded? That's my claim, theorem. So here's the way it works, is we pick epsilon equal to 1, right? Pick epsilon equal to 1 and giving, which gives some n, right? And the natural numbers such that what? Such that the absolute value of A sub n minus L is less than 1, right? Such that, n greater than n greater than n implies this, right? So if the sequence converges to something, that means we can pick n sufficiently large that beyond that point, we're within 1 unit of the limiting value, right? Okay, well, what does this mean? Well, this means that this is interchangeable with minus 1 being less than A sub n minus L being less than 1. All right? And what does that mean? Well, that means that L minus 1 is less than A sub n is less than, L plus 1. Right? For every n greater than n. All right? So, and of course, if they're strict inequalities, you can just as well throw inequality, right? It's still less than or equal to and greater than or equal to, right? Because it's less than and it's greater than. Okay, so check this out. I just let m equal to the minimum, right, of what? And I let big M equal to the maximum of what? So I'll start with the minimum. It can't be smaller than L minus 1, right? And it can't be bigger than L plus 1, right? Except what? This is good for what? This is a good little m and big M, above and below the sequence, provided you're before n. After n, rather. See, but up till the big N, up till big N, you could have something smaller or bigger. So what do? You just throw them in. See, I just throw them in. Like A1, A2, all the way out to AN. A1, A2, all the way out to AN. So in my example 3, this was a convergent sequence. It was bounded, right? So my L plus 1 would have been 3, L minus 1 would have been 1, yeah? And since n equals to 1, this construction would just have looked like, the minimum of 1 and the first thing, which was 3, and the maximum of 3 and the first thing, which is 3. So basically this, for that example, simply looks like 1 is less than or equal to a sub n is less than or equal to 3 for all n. I mean, that's what this argument looks like when we put it into practice for example 3. Okay, anyway, that's it. So that proves, because you can readily argue, you can readily see that in fact m is less than or equal to a sub n is less than or equal to big M for all n in the natural numbers. That implies then that the sequence is bounded. Now you might be wondering, what's the symbol I just used? I'm starting to use some symbols in here. I think you already know this is element of, right? Well, if you don't know yet, learn. This right here means for all. All right? So just so you know, that's what that symbol means, for all.
What's it called?
For all.
Is there a name for the symbol?
For all. Yes. Yeah, I don't know if there's yet another name for the for all symbol. It probably is, but it's not in my. I do not know. Yes, for every upside down A, there exists a backwards E. Yes.
What if you had a sequence that mapped out something with a vertical tangent line where one of the units?
Ooh, I don't know what a vertical tangent line is in here, because we're dealing with a discrete variable. We can't approach one point in the domain with arbitrary precision. We go 1, then we go 2, then we go 3. So there's no vertical tangents in this stuff.
But if one was undefined, would that mess up this?
Well, you have to, the first thing is that the a sub n's actually have to be real numbers. So if somebody gives you, here's a formula for a sequence, and when you plug in 3, it doesn't make sense, you should take that back to the store and return it, right? Or you should rejoice, because that question on your test will be omitted from the grading, because it's, or if, I don't know, or maybe I'll give bonus points if you're like, hey, I can't solve this problem, it's not even defined. Come on. Do your job. Write problems that make sense. Of course, I've never written a problem on a test which didn't make sense, so it's not relevant to me, of course, but sorry, I can't get through that without laughing. No, if I make a mistake like that, it's usually at the first step. So, all right, let me move along here. So, yeah.
Where did the 1 and 3 come from?
What I just erased.
6.
Yeah. So, if I apply this idea to example 3, the limit was 2.
Okay.
So if I do 2 plus 1, I get 3. If I do 2 minus 1, I get 1.
Okay.
And the n there was just 1. Actually, is it even that? I don't even think, I think n is, oh, it's even worse than that. I think that I think actually if you apply this argument to my example 3, it might even just be the first 2 terms that you need. Because n is 1, so I'd have to have 0 to have something before 1 in the sequence which starts at 1, right? Duh. All right, this is not important. So corollary to this, right? If a sequence is unbounded, then it is divergent. So for example, 5, I guess. What example am I on? 4. So there are lots of examples of divergent sequences. For here's one, a sub n equals to n squared instead of 1 over n, right? Right. This sequence, you can easily prove, is unbounded, right? Let me not prove that. Let me just say that it is evidently clear this is unbounded. Fine, how would you prove it? Suppose you have a bound, right? Caleb insists that you can bound it by 100, for example. And then I'd be like, no, you're an idiot. Oh, I'm sorry. Because I could put in 11 and get 121, which is bigger than 100, so your 100 bound fails. And you pick any number you like, right? You can always just go the square root of that number, like +1 round there is the integer that's going to ruin it, right? So it's unbounded, which means that this sequence diverges, right? Of course, we can be more specific. In fact, the limit as n goes to infinity of n squared, what's it equal to? Not only does the limit not exist, it's infinity, right? So infinity is that is to say it's a specific kind of divergence. All right. Now, question. If a sequence is bounded, is it necessarily convergent? So I've just told you that convergent implies bounded. Does bounded imply convergent?
Sine and cosine.
Sine and oh, good. Sine and cosine, very good. So no, right. So you're like sine and cosine. I like that. Because definitely for these, we've got -1 less than or equal to sine n, right? Less than or equal to 1, and likewise for cosine, right? So indeed, these are certainly bounded by ±1, and yet they are not convergent because they do what? They never settle down on a value, right? So I'm starting to use concepts we already had from before, right? What's my logic there? I'm using the continuous sine and cosine, right? That was my thinking. So we should talk more about that more systematically. So can I give an example here where I don't have to use that borrowing from the continuous world idea? How about this? Example 6. If I do a sub n equals to, let's say, -1 to the n, for n equals to 0, 1, 2, so forth and so on, right? This sequence is actually kind of boring, right? What's it look like? Yeah, exactly. It's positive, negative. It looks like this. It's 1, then it's -1, then it's 1, then it's -1, then it's 1, then it's -1. We get the idea. Like, let me write something a little bit more concretely. What we have here is we have that -1. Well, let me write it this way. I was about to use, oh man, this is, who just left this here? Like I might use it. Oh, almost. Whew, that was close. All right. So, how about this? A sub 2k is -1 to the 2k. A sub 2k plus 2k minus 1 is equal to -1 to the 2k minus 1, which is equal to what? So you're looking at -1 to an even power, right? 2k is an even number. That pretty much defines an even number, that there exists a k such that you can write it that way. So -1 to a, I mean, you can rewrite it, find one more step. -1 squared to the k, right? And this guy is -1 to the -1 times -1 to the 2k. So here you get 1 to the k, which is 1. Here you get -1 times 1, which is, of course, -1. Listen, however you want to sort through these, I don't expect you to work that out. I just wanted to prove to you that, in fact, we can do steps to show that that's 1 and -1 from the laws of exponents, yeah? Those kind of steps are important in other examples where it's not obvious from our intuition what's going on, okay? But so what's going on here is we have two subsequences, the even subsequence and the odd subsequence, right? What's a subsequence? So that's like a list within the list, right? A list within the list. And so here we have an even, so the even subsequence converges to what? Theorem, right? By the way. What's the limit as n goes to infinity of c? C, right? We could prove this, but you don't want me to, right? C. So I have to find a balance here. I need to prove some things, otherwise this course is not calculus 2. On the other hand, I can't prove everything because you guys will kill me. So, and I'll go insane as well. So like that wouldn't be good, right? But my point to you here is that the even subsequence is the constant 1. The odd subsequence is the constant -1. All right? So here's a tool for you. If you want to prove a sequence diverges, if you can find 2 subsequences, all right, which converge to different values, that suffices to prove the limit does not exist. If that happens, it's not going to infinity. If that happens, the limit just does not exist, all right? So when the limit's infinity, that's also a limit which does not exist as a real number, right? But this is explaining a very particular pattern, which is it's growing without bound, right? Likewise, minus infinity says that the sequence is growing without bound in the negative direction, right? This guy, on the other hand, we write this. If you're going to write something, limit as n goes to infinity of -1 to the n does not exist. And if you want to be more generous, you can say it does not exist due to oscillation, right? And the same would be true for the sine and cosine examples. So we get on this? So no, bounded is not enough to imply convergent, right? You need something more. You need what's called, well, to use a fancy word, monotonicity. But this is the bounded monotonic sequence theorem. The bounded monotonic sequence theorem says the following. It says that a bounded monotonic sequence converges. Moreover, there's 2 things that could happen. Number 1, if your sequence is increasing, and a sub n is less than or equal to m, then the limit as n goes to infinity of a sub n is less than or equal to m. You know, you might wonder what monotonic means, right? What do you think it means? This is a hint, right? I've said it's increasing, and part 2 is decreasing. So what do you think monotonic means? It's either what? It's either increasing or decreasing, all right? So if it's either increasing or decreasing, and you have m less than or equal to a sub n, then the limit has to be less than that. So this is the bounded monotonic sequence theorem. Now, so we can use this theorem to like calculate the limit of some things, right? So let's take aim at some, you know, relatively simple sequence to wrap our mind around. Let's look at the geometric sequence, okay? So this is example. We're going to apply this theorem to solve this limit, okay? So we had what? A sub n is equal to, let's say, c r to the n, and I'm going to put the absolute value of r to be less than 1, okay, just for the sake of discussion. So in this case, oh, and I need to be lazier than that for our current purposes. 0 less than r less than 1, that's better. Okay. 0 less than r less than 1. Okay, so then, think about this, is the sequence decreasing or increasing? Check this out. So if I look at a sub n plus 1, I've got c r to the n plus 1, right? But by algebra, that's r times c r to the n, right? Which is equal to what? R times a sub n. Is that less than, what, we have an inequality there, right? Because r is less than 1. So I can say that this is less than a sub n. What does that show you about this sequence? Is it increasing? Is it decreasing? What's happening? As we're increasing the index, the value of the sequence is getting what? Smaller, right? See this? A sub n plus 1 is smaller than a sub n. This was done for arbitrary n, thus, you know, a sub n is decreasing. Sequence, is it bounded? Yeah? What are the bounds? 0 and 1, very good. So 0 is less than a sub n, right? Which is equal to, again, cr to the n. And, oh, 1, oof. Okay, so in order to make life easier, let me add some, listen, we can take care of the case that c is negative in a minute here. Let's assume, to make life easier, c greater than 0. I think in my notes I had the good sense to put c equals to 1 for this discussion, and I forgot to do that here. My bad. All right? So let's suppose c is positive, and then we take your upper bound of 1 and we replace it with what? So this is less than c, right? Times 1, I mean, times 1 to the n, right? Which is equal to c. So in fact, this sequence is what? It is bounded, right? And it is monotonic because it's decreasing. Monotonic just means either increasing or decreasing, okay? That's all. So hey, this is a bounded monotonic sequence, which means that the limit exists. Aha! So hooray. Yay. How do you spell yay? Oh, like that, right? Yay. Limit exists. A sub n goes to L for some L. Now, we don't know what that limit is, right? I mean, we know that it's less than or equal to 0, right? And so if you look at this, all right, so anyway, but what is it? See, this is the thing about the bounded monotonic sequence theorem. It's a little bit subtle. It doesn't tell you how to calculate the limit, right? All it's done for us is told us that the limit exists. How is that helpful? So here's the trick. Remember what I told you? We had a recursive definition for the geometric sequence. What was it? Do you guys remember? We have a sub n plus 1 is equal to r times a sub n. I think I was on the way to saying that, and something happened and derailed me from saying it earlier today. My bad. I don't ever said that today, did I? Maybe I didn't. But this is true, right? Search your heart. Search your heart. This is true, right? This is how the geometric system sequence is defined. You take the nth one, you multiply by r to get the n plus 1th one, right? Alternatively, you could characterize, this is just the other side of the token, that a sub n plus 1 divided by a sub n was r. I did write that, right? We observed that. It was 3 for the one we looked at. Check this out. So what happens as n goes to infinity with this? What about this? The limit as n goes to infinity of a sub n plus 1, right, will be equal to the limit as n goes to infinity of r a to the n. What happens? What happens with this? What's that? Infinity. Well, there's no infinity here. We just proved that the limit of a sub n is L. So this, okay, and if you put n, if you replace n with n plus 1, is this the same? So there's a lemma to prove, but yeah, if you shift the index by 1 and you take, if n goes to infinity, what happens to n plus 1? Still goes to infinity, right? So this is L, and this, you can pull the r out, right? So this is RL. So what's the equation we have? We have L times 1 minus r is equal to 0. R is not equal to 1, right, by assumption. Therefore, L is equal to 0. So we have used then the bounded monotonic sequence theorem to prove that the limit as n goes to infinity for positive c times r to the n is equal to 0. And that's a pretty typical use of the bounded monotonic sequence theorem. I think I should use the projector here for the next example, just so I don't hurry it, and we can look at the calculations together. Okay, guys? So if I can find it. I did post what I'm about to project here in Canvas, so, oh man. What's it doing to me? Error. Well, hopefully this works. So, I mean, this example is simple. I think this is one of your homework problems, by the way. I asked you to prove that the limit of the geometric sequence is what it is. This is one case of that proof. There are other cases, okay? What would the other cases be? You could have r equals to 0, right? You could have r having, you know, absolute value less than 0, but greater than -1. It's relatively obvious that if you look at the case that the absolute value of r is greater than 1, what can you tell me about that sequence? Think about this while I'm finding stuff. Think about this. If the absolute value of r in that last example was greater than 1, what could you tell me about the sequence? Let me ask a leading question. Is it bounded? Think about that. If you have cr to the n where the absolute value of r is larger than 1, is it a bounded sequence? No, it's not. So then that sequence diverges if the absolute value of r is greater than 1. If it's equal to 1, what happens? It just gives you back c again, right? Because it'd be like c times 1 to the n, which would just be the constant sequence c, actually. I sure hope I put it in here. Otherwise, we're in trouble. Oh, here it is. All right, let me get it out of this miserable... Where's my download? There we go. I prefer to look at these things in Adobe. All right. I will eventually get this set up right here. So I wanted to write out that one. So I have the proper definition of monotonic in the notes, of course. I didn't write it on the board, but so we just worked example 1.14, all right? Example 1.15 is perhaps more interesting. So here we're looking at the sequence defined by, it's all good. I guess I just, there we go. So I can make this slightly bigger. So, you know, as I should mention, as I'm working a homework problem, if I'm not sure, if I don't have an intuition about what the nature of the sequence, like the first thing I do is get a calculator out and I start crunching some numbers to see what happens, all right? So like this one's defined kind of weirdly. A sub n is the square root of 2 times a sub n minus 1, right? So this is a recursively defined sequence. Here's the first couple things. Like a sub 2 would be the square root of 2 times the square root of 2, like this, right? That works out to 1.68. And then the square root of the 2 times the square root of the 2 times the, like this. I can't even put it in English, right? That it works out to 1.83. And then a4, like this, 1.91, right? And so maybe if you keep going, you'll find the fifth one is 1.95, the sixth one 1.97, the seventh one 1.98, the eighth one 1.99, right? So if this is the test question and you punch all these things in and you tell me, hey, the limit's 2. This is worth something, right? About 30% of the credit is what that's worth. It's worth something, though, right? The full answer, though, should be using what? The bounded monotonic sequence theorem for full answer. So like, so here, you can prove that it's bounded. It's, 0 is less than the sequence, and look here. So if you notice that a sub 1 is equal to square root of 2 is less than 2, right? And suppose that a sub n is less than 2, all right? Look at a sub n plus 1. A sub n plus 1 is equal to 2 times the square root of 2 times a n. Why? It's like this building is like shaking its leg. Like, what's up with this building? Anyway, I guess that's what happens when you hang projectors from like the ceiling. But anyway, is it just me, or can you also see the screen wobbling? Okay, good. Whoa, sorry, I should not focus on that. Anyway, my point is that this is less than 2 times 2 by assumption, right? I'm assuming that a sub n is less than 2. So if a sub n is less than 2, that implies that a sub n plus 1 is less than 2 as well. But n was arbitrary. What does this mean? This means that a sub n is less than 2 for all n. This proof I'm giving you is called a proof by mathematical induction. You assume something's true for n. You show it's true for n plus 1. If you've also shown that it's true for the base case, then that means that you've proved it for all n, right? This is called proof by mathematical induction. Okay, so there we've shown that it's bounded by 2 and 0 below, and it's increasing, right? So you can, is it increasing? Yeah, it's increasing, right? You can see that it's increasing from its recursive definition. Therefore, by the bounded monotonic sequence theorem, the limit exists, right? So the showing that it's increasing and bounded, that's about 30% of the credit, all right? So the answer is about 30% of the credit. Showing it's bounded and increasing, that's about 30% of the credit. The other more interesting part is actually calculating the limit, and that's also worth about 30% of the credit. So like there's a lot of different things going on here. So this is the recursive relation, right? And if you take the limit as n goes to infinity, what happens? This goes to L, and this goes to, well, the square root of 2L. And then you can solve for the limit, even though we don't have a formula. And if you do that, you get L times L minus 2 equal to 0, right? So either L is equal to 0 or L equal to 2, but obviously the terms of the sequence are increasing, which disallows 0 being the limit. And that forces us to find the limit, it's 2. Yeah.
On example 7, in the step where you said that a n plus 1 is equal to r a n, how did you determine that?
This?
Yes, sir.
Oh, well, an was defined to be cr to the n. So I'm just identifying. I wrote here. So that is that literally.
Mm-hmm. And then why'd you put the r in front of them? How did you separate them to each other?
Well, there's r's here. So that r is this r.
Well, I know, but why'd you put it there? Like, how'd you get it there? Because, like, to the left of that, you had CR.
Oh, well, r to the n plus 1 is equal to r times r to the n, right?
Okay.
Okay, so there we go. Yeah. It's all good. Okay, so listen, I'm spending a disproportionate amount of time talking about the bounded monotonic sequence theorem because this is new, right? You've never heard of this thing before, I'm guessing, unless you had a really good, like, AP calculus or whatever. So I wanted to spend some time talking about that because I think it's weird. The argument I just went through is weird, right? Oftentimes, to calculate sequences, we don't need something so weird, all right? Like, there are simpler things, and so let's look at those. And so, for example, sometimes we can use calculus to bound a sequence. So here's one. I have the square root of n plus 1 minus the square root of n, right? So that is not, why is that ambiguous? It's ambiguous because you're looking at infinity minus infinity, right? You guys remember? So if I look at the corresponding function, right? If I replace n with a continuous variable x,